Welcome to Geo Remore. I'm Robert Johnson, your friendly host. We cover everything from world affairs to breaking news and global conflicts. Remember to hit subscribe, also leave a comment and turn on notifications. This way, you'll always catch all of the episodes, and if you enjoy the show, please share it with your friends and family. But before we start, we want to make it clear. The views in this podcast are only of the speakers. They don't always represent the opinions of Geo Rumor or its affiliates. We want to keep things honest and transparent. Thanks for tuning in. Planning and design are critical for bridge construction. They set the foundation for the whole project. This phase ensures the bridge meets the needed specs. It also fits with environmental, economic, and social needs. Here's a deeper dive into the two main components of this phase. Feasibility studies. Feasibility studies are thorough. They help determine if the proposed bridge project is viable and worth doing. These studies cover a broad range of factors. Environmental Impact Assessment, EIA, evaluates the possible environmental impacts of the bridge. It looks at factors such as effects on local wildlife, water, and the ecosystem. Mitigation strategies for adverse impacts are also developed during this phase. Cost analysis. A detailed cost analysis includes initial construction costs, long-term maintenance, and operational costs. This analysis helps in budget planning and securing funding for the project. Technical requirements. Engineers assess the bridge's technical challenges. These include the soil type, water currents, and weather. The plans also indicate the expected load that the bridge will carry. This assessment helps understand the engineering solutions needed to address these challenges. Societal and economic benefits. This involves evaluating the benefits of the bridge. It could improve transportation links, cut travel time, and create economic opportunities. It also looks at the impact on society. This includes any displacement of communities. It also covers measures to reduce these impacts. Design phase. The studies confirm the project is viable. Then, the design phase begins. This phase is where the conceptual vision of the bridge starts to take a more concrete shape. Selection of materials. Engineers decide on the materials. They base this choice on strength, durability, maintenance, and cost. Common materials include steel and concrete. Sometimes, parts of the bridge use timber or advanced composites. Type of bridge. Engineers select the type of bridge based on the span length. It can be a suspension, cable-stayed, arch, beam, or truss. It is also picked based on looks, the environment, and budget limits. Each type of bridge offers specific advantages and is suitable for particular situations. Engineers choose suspension bridges for long spans. This is because there are few places for piers in the water. Arch bridges blend natural strength and beauty. They are suitable for shorter spans and scenic locations. Beam bridges are simple and cost-effective for short distances. Cable-stayed bridges have a striking design. They also have an efficient way to distribute forces. This works well for medium to long spans. The design must accommodate many loads. These include the weight of the bridge, dead load, and the weight of moving vehicles, or trains, live load. There are also environmental loads: wind, earthquake, ice. Finally, there are dynamic loads, vibrations and impact forces, safety and accessibility. The design has safety features. It ensures access for all users. This includes pedestrians, cyclists, and, as needed, people with disabilities. The planning and design phase is iterative. It involves ongoing talks among engineers, architects, environmentalists, and stakeholders. The goal is to refine the bridge's design. People often use advanced software tools and models. They use them to see the bridge design and test its performance under various conditions. This allows for adjustments before physical construction. This planning and design process is careful. It ensures the bridge meets current needs and can handle future challenges. Building a bridge's foundation is crucial. This is especially true when it involves water. During this phase, the project faces the water challenges directly. It lays a stable base for the rest of the structure. Let's delve deeper into the techniques you mentioned. Cofferdams. Cofferdams are temporary enclosures in water. They facilitate the removal of water and establish a dry work area. People use them to build foundations. They are particularly useful in shallow water conditions. Construction materials. You can make cofferdams from steel sheet piles, wood, or concrete. The choice depends on the project's needs. We include the depth and conditions of the water and the size of the area that will be enclosed. Process. Driving the chosen materials into the waterbed soil makes the enclosure. They form a watertight perimeter. Once the perimeter is secure, pump out the water. This reveals a dry work area. Usage. Contractors use cofferdams for more than bridge foundations. They also fix ships, make docks, and perform other underwater projects. Challenges. Key challenges include stopping water from leaking into the work area. They also include managing the impact on the aquatic ecosystem. Pile driving. Pile driving is key for making a deep foundation. This is especially true in areas where the soil can't support normal foundations. Piles. Piles are long, slender columns made of steel, concrete, or wood. They drive them deep into the ground to reach a stable layer of soil or rock. Pile drivers. This machinery drops a heavy weight from a height. It's called a drop hammer. It can also use a hydraulic hammer to drive the piles into the ground. One can also use vibratory pile drivers, which vibrate the pile down through the soil. Considerations. The length and type of pile depend on the ground, and the load the bridge will carry. Pile driving in water needs special equipment. It also needs special care for noise and vibration. These can harm sea life. Caissons. Construction workers use caissons to build foundations in deep water. Traditional methods are not possible there. Structure. A caisson is a large, watertight box or cylinder. It is usually made of steel or reinforced concrete. Installation. Workers take caissons to the site and sink them to the desired depth by digging out the soil from inside. This process continues until the caisson reaches a firm soil layer or bedrock. Concrete filling. Once the caisson is in place, fill it with concrete. This forms a solid, immovable base for the bridge's piers or columns. Types. There are several types of caissons. These include open caissons, box caissons, and pneumatic caissons. At the top, they seal and pressurize pneumatic caissons. This allows workers to dig dry soil below water. Challenges. Working with caissons can be tough and requires careful risk management. Caisson work has many dangers. For example, decompression sickness can occur in pressurized conditions. Each technique for building foundations involves complex engineering and careful planning. The goal is to ensure the bridge can withstand nature and time. The choice depends on many factors. These include water depth, soil, impact, and the bridge's needs. The options are cofferdams, pile driving, and caissons. These foundations bear the bridge's weight and ensure its long-term safety. Building the substructure is critical. It includes piers and abutments. This phase impacts the bridge's longevity and safety. This phase ensures the superstructure will have a stable base. The base must also be durable. Construction of piers are the main vertical supports for bridges. They move the load from the bridge deck to the foundation below. The construction of piers involves several key steps and considerations. Material selection. Piers are commonly constructed from concrete or steel. Reinforced concrete is widely used for its strength and durability. You can mold it into various shapes. Steel piers are rare. Their high strength to weight ratio and fast construction times make them useful. Design and engineering. The pier's design considers the loads they will carry. These include the dead load, the weight of the bridge. There are also live loads like vehicles and pedestrians. There are also environmental loads like wind, quakes, and water flow. The piers are also designed to be small and in the right shape. They make them this way to block water flow as little as possible and to reduce harm to the aquatic environment. Construction techniques. You can build piers in place using formwork. Workers pour concrete into the formwork. Or they can be precast in a factory and moved to the site. The chosen method depends on the project's specific conditions. These include accessibility, water depth, and the environment. Foundation connection. The base of the pier is firmly connected to the foundation. The foundation can be a footing, piles, or caissons. This connection ensures stability against tipping and sideways forces. Construction of abutments are at the ends of the bridge. They move loads from the deck to the ground. They also hold the embankment. They are crucial for the bridge's stability and alignment. Functions. Abutments support the bridge ends. They also stop the embankment from washing away. They give side support to the bridge. And they connect the bridge to the road at each end. Materials and design. Like piers, abutments are usually made of reinforced concrete. Its strength and versatility make it useful. Abutment design considers the bridge type, terrain, soil, and water. The goal is to ensure enough support and durability. Construction. Building an abutment often starts with digging to the needed depth. Then, we prepare the foundation. This may involve pile driving or laying a concrete footing. The abutment walls are then built. This can involve pouring concrete or assembling precast components. Considerations for both piers and abutments' environmental impact. Designers and builders both design and build piers and abutments. They do this to limit the structure's impact on the environment. This is especially true in water. This includes designing structures to stand up to water. Where possible, they should also reduce harm to local ecosystems. Aesthetics. Piers and abutments are visible, so their design often considers beauty. This is especially true for bridges in important places or with great architecture. Durability and maintenance. We choose materials and methods based on their ability to last. They need little maintenance. We consider factors like corrosion, freeze-thaw cycles, and wear. Building piers and abutments is complex. It requires careful planning, precise execution, and coordination between engineering disciplines. This will make sure the bridge is safe. It will also make sure it is durable and works for its intended lifespan. The superstructure is the part of the bridge that spans the gap between supports. It also carries the load. Building it is when the bridge starts to take its final form. This phase uses many methods. It depends on the span's length, the materials, and the bridge's design. Girder placement. Girders are horizontal structures that support the deck of the bridge. They are fundamental in transferring the load from the deck to the piers and abutments. Materials. Girders often use steel and pre-stressed concrete. They choose them for their strength and durability. Process. Cranes lift girders into place. Contractors may bolt or weld steel girders together on site. Pre-stressed concrete girders are typically precast. They then move the items to the site where they lift and connect them. Types of girders. I-beams and box girders are common types. Box girders are hollow, rectangular beam structures. When people need higher torsional rigidity for longer spans, they use them. Segmental construction. Segmental construction is a method for building longer spans. Building the bridge in one piece would be impractical. Prefabrication. Segments are either cast in a factory, off-site, or cast on-site in a temporary casting yard. Building off-site has the advantage of controlled conditions. They can improve quality and speed up construction. Transportation and assembly. Workers take the precast segments to the bridge site. Then, cranes or launching gantries lift them into place. Strong epoxy glue and tendons connect the segments. The tendons thread through ducts in the segments and then tense. This process compresses the concrete and adds to the bridge's strength and stability. Advantages. This method allows for fast construction. It has minimal impact on the environment below the bridge. This makes it ideal for crossing busy roads, waterways, or sensitive areas. Cable-stayed or suspension bridges spans may be too long for simple beam or segmental bridges. Engineers may choose cable-stayed or suspension designs. Cable-stayed bridges. Feature towers, pylons, from which cables directly support the bridge deck. The cables attach to the deck in a pattern. It can be harp-like with parallel cables or fan-like with cables that spread out. This design allows for spans of up to around 1,000 meters. Construction. First, builders construct towers. They are often built using slip forming. Workers continuously pour concrete into moving forms. After placing the towers, workers attach cables from the towers to the deck. They often build the deck incrementally outward from the towers. Suspension bridges. anchor cables at each end of the bridge and pass them over the tops of high towers. The main cables hang freely between the towers. They create a catenary curve. Vertical suspender cables carry the weight of the deck. Construction. First come the anchoring systems. Then come the towers. The main cables are then spun. In this process, steel wires are strung across the span and bundled to form the cables. Finally, we attach the deck using the suspender cables. Innovations and challenges, engineering challenges. The superstructure requires precise engineering. It must ensure the bridge can handle static and dynamic loads. These loads include wind, traffic, and earthquakes. Innovations, materials science has advanced. This led to the development of high-performance concrete and weathering steel. They allow for longer spans and more durable structures. Also, CAD and CIE software has improved bridge design and construction. It has made them more efficient and accurate. Building the superstructure is a striking part of bridge construction. It shows the clever engineering and teamwork needed to span vast distances. The structures they create are functional and often iconic. In the decking and finishing phase, the goal is to make the bridge's surface. Vehicles, pedestrians, or trains will use it. The phase also ensures the bridge is safe, strong, and ready for use. This phase encompasses several critical processes. Construction of the bridge deck materials. The materials used for the bridge deck depend on the type of bridge, its use, and the budget. Common materials include reinforced concrete, steel, timber for pedestrian bridges, and composite materials. Process. For concrete decks, builders set formwork to define the deck's shape. They then place rebar or post-tensioning tendons and pour concrete. For steel decks, people often use prefabricated steel deck panels. They then weld or bolt the panels to the girders below. Waterproofing importance. Waterproofing is crucial for protecting the bridge. This is especially true for concrete decks. Water can get in and cause the steel inside to rust. This rust can lead to the bridge falling apart early. Methods. Membranes can achieve waterproofing. They are either laid on top of the deck and beneath the paving layer or integrated into the concrete deck. These membranes must be durable, flexible, and weather and traffic wear resistant. Paving, asphalt, paving. These bridges are for vehicles. They have an asphalt overlay over the waterproofing. The overlay makes a smooth, tough surface. It can handle traffic and conditions. Concrete finishes. Some bridges may use a concrete wearing surface. This is common in busy or industrial areas. People use it because it is durable and requires little maintenance. Safety features, railings and barriers. Safety railings are on the edges of pedestrian bridges. Vehicular bridges have guardrails or barriers. Designers create these barriers to stop vehicles from leaving the bridge. Designers created these features to meet safety standards and regulations. Lighting. Adequate lighting is crucial for ensuring the safety of all bridge users. The lighting system's design considers factors. It aims to minimize glare, save energy, and fit the area's look. Sidewalks and bike paths. Multi-use bridges often have separate pathways for pedestrians and cyclists. These paths provide a safe space away from cars. Finishing touches, signage, and markings. The signs, lane markings, and other road markings guide bridge users. They ensure safe navigation across the bridge. Landscaping and aesthetic elements. Many times, people landscape the areas around the bridge. To enhance the bridge's appearance, designers add aesthetic elements. They help it blend with the environment or stand out as a landmark. Inspection and testing. Before the bridge opens to the public, inspectors test it. They make sure it meets all safety and performance standards. This includes checking the deck's integrity. Also, the waterproofing is effective. The railings and barriers are strong and stable. Lastly, the adequacy of the lighting. Decking and finishing come next. They turn the bridge from a structure into a usable part of the infrastructure. This phase needs close attention to detail. It is to ensure that the bridge serves its purpose well. It must do so safely and efficiently for its expected service life. Inspecting and opening a bridge marks the end of a complex planned project. This phase ensures the bridge is safe. It meets all rules and quality standards, and it is ready for public use. Here's a more detailed look at the processes involved. Comprehensive inspections. Before a bridge opens to the public, it undergoes many inspections. The checks verify that each part of the structure meets the safety and quality standards. Teams of engineers and inspectors conduct these inspections. They may involve several types of assessments. Visual inspections. Inspectors examine all parts of the bridge. This includes the deck, piers, abutments, bearings, guardrails, and lights. They look for any visible defects or problems. Structural inspections. These involve checking the bridge's structure. They ensure that all parts can carry the expected loads. Inspectors may use many tools and techniques. These include ultrasound, magnetic particles, and dye penetrant. They use them to find cracks, corrosion, and other weaknesses. Functional testing. This includes testing movable parts, if any. For example, drawbridges or swing bridges. It also includes testing safety features like lighting and drainage systems. Load testing. Load testing is not always required, but it can verify the bridge's capacity to handle expected traffic loads. This involves putting heavy loads on the bridge. Or using special vehicles to simulate normal and extreme traffic. Safety and regulatory compliance. Compliance with standards. Inspections ensure compliance with standards and rules. They apply to bridges. The rules are national and international. They cover construction and safety. This may include standards related to materials, design, construction practices, and environmental protection. Documentation and reports. After conducting the inspections, we compile detailed reports. They document the findings and any needed corrective actions. These reports are essential for the certification of the bridge for public use. Corrections and final preparations addressing deficiencies. Inspections show problems. They must be fixed before the bridge can open. This might involve repairs, reinforcements, or other corrective measures. Pre-opening preparations. The final preparations include cleaning the bridge. They also involve removing construction equipment. They also involve adding any remaining safety measures. These include road markings and signs. Official opening ceremony. A new bridge opens with a ceremony. The ceremony is to thank all who worked on the project. It also marks the bridge's importance to the community it serves. Public access. Once officially opened, the bridge opens to the public. Depending on its design, it may be for cars, walkers, bikers, or trains. Post-opening monitoring, initial monitoring. After the bridge opens, engineers often watch it closely. They focus on its performance, especially under real loads. This monitoring can help identify any immediate issues that require addressing. Regular maintenance and inspections. Even after opening, bridges need regular maintenance. They also need periodic inspections. These checks ensure they stay safe and strong during their service life. Inspecting and opening a bridge is a critical final step in its construction. It marks the project's shift from a construction site to an infrastructure. It shows the importance of safety and quality in civil engineering projects. They ensure the bridge will serve its purpose well and safely for many years. Building bridges, especially over waters, need special considerations. These are to address the environment and to ensure safety for navigation. These ideas are key to the planning, design, and construction phases. They also matter for the whole life of the bridge. Environmental impact. Minimizing the impact of bridge construction on the environment is crucial. It protects ecosystems, preserves water quality, and keeps the natural landscape. Here are key strategies and considerations. Environmental Impact Assessments, EIA. We should conduct full EIAs before construction starts. These studies find potential impacts and ways to reduce them. This includes studying impacts on local wildlife, aquatic ecosystems, vegetation, and water quality. Sediment and erosion control. We will implement measures to stop sediment from construction. It can harm waterways, aquatic life, and water quality. This may involve using silt curtains, sediment basins, and erosion control blankets. Construction methods and materials. selecting construction methods and materials that reduce environmental disruption. For example, you can choose materials with lower carbon footprints. You can also use methods to make construction take up less space in sensitive areas. Restoration and mitigation projects. Restoration projects are undertaken to rehabilitate disturbed natural areas. This might include planting native plants again. It could mean making artificial reefs, or it could mean fixing habitats that the construction harmed. Monitoring and management plans. The programs will monitor the bridge's impact. They will do so during and after construction. Their goal is to ensure compliance with environmental rules and promises. Navigational clearance for bridges over navigable waters. Ensuring enough clearance is vital. It allows safe and free passage of boats and ships. This involves several key aspects. Regulatory compliance. It adheres to national and international standards and regulations. These regulations specify the minimum clearance for waterways and vessels. They ensure that bridges do not block commercial and recreational navigation. Design considerations. The bridge must have enough room under it for ships, and enough space between its supports. The design must account for the biggest vessels that will use the waterway. It must consider both current and future needs. Aids to navigation. We will install navigational aids, including lights, buoys, and signage. These aids will guide boats safely under or around the bridge. They prevent accidents, especially in narrow or crowded waterways. Movable bridges. In some cases, bridges have movable sections, which let larger vessels pass. Examples include drawbridges, swing bridges, and lift bridges. Movable bridges need complex systems. They ensure the bridge's reliability and safety. Coordination with maritime authorities. They collaborate with maritime authorities to set navigation protocols. This is especially important during construction. Temporary structures or equipment may limit space. This includes talking about construction schedules, temporary closures, and any changes to routes. Meeting these needs requires a team from many fields. It needs environmental scientists, engineers, maritime experts, and regulators. Adding these ideas to planning and design can cut bridge projects' environmental impact. They can also fit well with nature and human-built areas. This will ensure safety and sustainability for years to come. Thanks for watching. If you love diving into today's video, hit like to let us know. Ready for more? Click subscribe and tap the bell for the freshest updates. Don't miss our latest gem in the Fresh Off the Press playlist. For more intriguing tales, check out our other videos. Your next favorite story awaits. Before I say goodbye, I wanted to remind you of a few things. If you enjoyed this podcast, be sure to subscribe. Also, comment, like, and share it with your loved ones. And turn on notifications. I love having you with me. I want to keep exploring the world of world affairs, breaking news, and the complex web of global dynamics. I want to do it here at GeoRumor. Also, all the information I provide in this podcast is for general info only. I do so with good intentions. Thanks for tuning in to GeoRumor. I appreciate your support and hope you learned something new today. Remember to keep the global conversation alive.